All right. How you doing, everybody? Sorry about last week. It was last week was just not my week in general. It did not go my way in a lot of different ways, and so that included just not a live stream last week just wasn't going to work out. So I didn't get to it. Anyway, we're here this week. Hope you're having a great week. Great start to your week. Hope you had a good weekend. Hope your football team did what you were hoping. If not, I'm sorry. I guess I don't know. I do need to change the fuse out. So I love this meter, right? This is an excellent meter. I've had this thing for a really freaking long time at this point. It's the LT17A. To my knowledge, I don't know if Field Piece even makes these anymore. I think you can still order them online through various means, but I don't know what their actual official support is. But you can still get the little fuses, just like what is it, the HS36 meter. Anyway, I love this one for a couple of reasons. One, I really like the manual dial, especially if I'm doing like precision, which is what I use this meter for. Like, this is my precision testing, and if I am if I'm doing just general like field troubleshooting testing work, stuff like that, I'm not worried about it. I've got a little UEI Phoenix something or another that I use for that. I'm not too worried about that kind of stuff. What I get worried about is whenever I have to do like precision stuff. So we're talking drive troubleshooting, capacitors, circuit boards, doing really in-depth detailed stuff. That's where I pull this thing out. So I love being able to manually choose all my ranges, so I know exactly where I'm at. But then on the microfarads here, I can go up to 20,000 microfarads, and I find that it's a pain to find a meter that has a range that high. There is only one machine I've ever come across that had higher than 20,000 microfarads on the capacitor bank. It was like 24,000. So I had to get creative with the troubleshooting there. I'm trying to remember what machine that was, and I don't remember which one. Anyway, so I need to put a fuse in. I thought, hey, you know what? Why not? It'd be a fun kind of open the stream with doing a fuse replacement, because one thing I'm horrible at, I've done this so many, I can't tell you how many of these fuses I've gone through over the years. I'll end up I'll have, so the meter goes over here whenever you're doing microfarad testing, right? And the leads go here. So I'll test the capacitors, and then without thinking about it, something will happen. I'll go back, reference material, read, whatever, and I'll forget. And I'll switch back over to volts, and then I will try to test the voltage without moving the lead back over to the volt side. And what does that do? It blows the fuse immediately every time. Every time. So that's probably one of my only complaints, and it's more of just an oversight on my part, is doing that. So I don't know. Has anybody else used a meter like this, or do you have, like, what is your preferred service meter for like in-depth stuff like this? You know, which one would you go with, or would you choose given the option? I'm actually kind of curious. I'm not opposed to like switching to a different one at some point, especially like it's just a matter of time before this one just calls it. Like, I've had this thing for a long time, and like, it's been through some stuff, right? It was my daily service meter at one time, so like, it for a period of time it did go through some pretty rough routine abuse before, you know, I switched to what I call my beater meter for the daily stuff. I don't know. Anyway, let's get this open. You know what I should have grabbed? Come on. I'm trying to remember. It should be this fuse, I think. So I've got the spare fuses. We're gonna change both of them because now that I forgot this second one was in here because it's been a while since I've had to change this. We're just gonna change them both out, and then no touch. Nope, no touch. Okay. And then we can test which one is the actual bad one. I'm pretty sure it was this one. So put these over here. He's got the Fluke 902. So does that one do capacitance? The 902 FC. I'm not against Fluke, but I'm also not in their not read up, I guess, on everything they offer. Here. Okay, so we got 2 new fuses in. I don't have a capacitor here in front of me to test with. That's fine. We don't have to do all that right now. We'll just put this back together. All right, so what's the, on that Fluke, what's the capacitance range? Like how high can you go? Because most of them I look at, they max out at like 1,000 microfarads, which is like for what we're doing on the chiller side, that's not enough. Like if you're spending all your time on lighter equipment, RTUs, splits, reach-ins or walk-ins, stuff like that, 1,000 microfarads is fine. Like that's not going to cause you any issues. But you start getting into chiller drive troubleshooting, most of those are in the tens of thousands of microfarads, or I say tens, between 10 to 20,000 is where most of those are that I've worked on. So, do you know what the max is for that meter? I can look it up here in a minute. If not, I'm just curious. And feel free, anybody has any questions, go ahead and get them posted. We do have a question from the CQA portal, Chiller Questions Answered portal on the Chiller Academy. So I try to prioritize that. If you can always, if you're wanting your questions like for sure gotten to, and you want to have any kind of in-depth discussions, things of that nature, getting into that portal is the best place to do that in the Academy. And you can post your questions there. And I do get a notification. I do see them, and I try to follow up with them on stream. Sometimes I follow up with you ahead of time, kind of discuss it first a little bit, and then maybe go a little bit deeper on stream, or at least review what we discussed. So feel free to make use of that. So the first question, by the way, is going to be over the 30XWHP by Carrier. So we'll get to that in just a minute. I've got some thoughts. Just manufacturers playing games. Okay. So we should be good. Does it turn on? It does. Okay. So we need to go to ohms. Go to 200 ohms. And then let's see which of these was our bad one. I'll throw that one away. Okay. That one's should be good. Oh. Okay, that doesn't make sense. Here. Maybe the whiteboard is allowing some kind of conductivity. I do have my finger off of it there. Okay. These were blown. One of the one of them was blown. Well, how do I trust either of them now? Because I just used this the other day, and I forgot several months back it had blown. I hadn't had to use it. I switched over. Why is it not? Huh. Okay. Tell you what, I'm gonna set these aside. I'll deal with that later. I expected to see OL on one of those because one of them is bad. Or at least I thought it was bad. Maybe I did something wrong that particular day, and I just don't remember. Who knows? Either way, I see we've got Miss HVAC Time herself in the chat, Miss Lioness there. I'm glad you like my meter, babe. I like it too. All right, so we got 1,000. I have an offer to go work on chillers at the Union. Excited but worried. Okay, so let's discuss that, Cody. We'll dive into this just before we get into the official questions. So, what is your what are you concerned about with going with the Union? And do you mind sharing kind of what region? You don't have to get real specific with where you are, other than just are you in the East Coast, West Coast? Because I do find with a lot of the discussions that the unions per each region tends to fluctuate quite heavily in the feedback I get on people's experience with that union in particular, right? So, like, what region kind of are you in? And then what are your worries? Let's dive into that. Because you got to think, it can be it's a big deal. And it can be a very different career path. So at some point, going the union path and going the non-union path, which I went the non-union, in my area in Texas, going union was just not really even an option. Not until I got into the big cities, but I didn't start off in the big cities. So by the time I made it to the city where the unions actually have any kind of a presence here, I was already far enough along in my career. It just didn't make sense to go through the union. Not that I was really interested in doing that to begin with. That's just me, my personal preference. And I'm in a region where, like, you don't have to go union to be, relatively successful. There are a lot of regions, though, that they're very locked down, hardcore union, right? And so it's not that you can't have success if you're non-union, but it's very challenging because a lot of customers are like, they've got internal agreements that they won't hire non-union contractors anyway. All right, so it's with local 420, Harrisburg, Pennsylvania. They want me to take a little bit of a pay cut. I'll enter as a serviceman, taking an apprenticeship test in 6 months to see where I'm at. Yeah. So what is your, like, how much time do you have prior to this, Cody? Have you been through trade school? Are you coming from light commercial residential? Have you already been in the trade? I know in Pennsylvania, yeah, that's a very unionized region, very much so. And interestingly, from what I've heard, that specific part of the Northeast doesn't do too bad on the union side, from what I've heard. Now, I know that you get a little bit further south, I've heard some pretty sketchy stories. You get more into the Midwest and Central, again, pretty sketchy areas. Maybe not every hall, but enough of them to be cautious, right? So, yeah, I'm very curious as to what your experience is coming in, because that's part of my issue I have as somebody with experience trying to get in with the union is there. It gets back to just the gatekeeping thing, and yeah, basically, if you don't follow it I don't want to be mean, right? It comes back into it just comes back to regional differences. So I do refrigeration, supermarket racks, only 2 years. I have a degree. Okay, so you've got some, and especially if you're doing rack systems, you've got some very legitimate experience. yeah, sure, you're 2 years into racks, but with having gone through school and then being able to do rack, I'd say you're pretty well on your way. The thing that the unions are very heavily on the industrial side, very heavy on the just the heavy commercial side of things. So they're going to be really interested in your ability to manage hydronic systems. That's going to be a lot of what you work on. Not everything. You're still going to have RTUs. You're still going to have all the basic uh, work that we would try to service. Um, yeah, it's the whole. So here's one of the big arguments that you'll see, and I think it does have some merit on the union side. So while technically you may take a little bit of a pay cut hourly, most unions, especially the good ones, the halls, offer really good benefits packages. They do. That's from a non-union side, competing with them for like hiring people. That was a major challenge I've always faced. Was it was very difficult to match the benefits packages that the local unions could provide. That's just how they're built and how they function. So you could see that you could argue that there is a trade-off there, but see, here's one of the things that I think we should remember is not all benefits are just because they offer benefits doesn't mean that provides you legitimate value, right? Um, that's one of the issues I see with the whole benefits conversation is this whole benefits package. There may only be a small portion of this package I actually care about or I'm actually interested in long term. And whether I should or shouldn't be from the retirement standpoint to the medical benefits, whatever, it's not really the point. Just because it's important to somebody else doesn't mean it's important to me. They've got different life circumstances than I do. So I think the whole hiring marketing shtick around that is something to be um, thoughtful of. I'll say it that way. So in terms of the pay cut, but there again, if you're coming from a good company that maybe has some legitimate size, can offer some decent benefits, then it's not that big of a the benefits that you're getting from the union may not be as big of a jump as if you're coming from just a real small shop or something to that degree, which if you're doing rack systems, depending on most of the shops that I've worked with or I know that do work on racks and that is their primary source of service tend to be larger shops most of the time. That's a very difficult market to get into and to compete with. And so it's usually just the bigger players that end up working out in the end. Like they're the ones who have those clients, those customers, yada yada. So you may already have a pretty decent benefits package. One of the things that I would hate though, so you've already gone through school. Then they're going to make you go through 6 months of basically field work to fill you out. Do they even like you? Are you going to fit in the culture of the union? Like that's the kind of thing that they're evaluating with that 6 month window. And if they don't feel that you're going to buy into the whole union thing, then they may not accept you. And that may be at the halls level. I'm not an expert on this, but some of these decisions aren't even up to just the companies you're working for. Some of this comes back to the actual leadership at the hall itself and who they are and aren't going to accept into their programs. And that then they want to put you back through an apprenticeship and maybe your apprentice test, you do a good enough score, but maybe you don't pass all the way. And so then you go from, okay, maybe you get to skip year 1 and 2, but you still got to do 3, 4, and 5 as an apprentice before you even get to take your journeyman's test, right? I personally just I don't fit in those environments. Here's part of my issue. And here's a bias that I have. Okay. I don't fit in those environments. I don't work well in those corporate scenarios. I'm just not one of those people. That doesn't mean I'm right, you're wrong. That doesn't mean that this is a bad fit for you. It's hard for me to give unbiased advice here because like I don't even work at big companies. I've almost always kept myself to smaller shops, smaller teams, because my personality just doesn't mesh well in a corporate environment. Like the having to cut through the red tape and all the BS and the process there just doesn't jive with me, and I get very frustrated, and it doesn't work to my benefit. So I've learned to avoid it. The early on corporate style jobs I had taught me that that's just not my world. So I don't know if I've said anything that's going to give you any benefit. How you doing, Jason? I see you there, bud. Yeah, it's a tough thing, Cody. I'm happy if you want to follow up and maybe have a more of a discussion off the stream. That might be helpful. Maybe I could give a little more of a direction. For me, like, so when it comes down to just a pure, say, logical decision on what do you want out of your career, what do you want to work on, what do you see around you, um, what do you already have, why do you want to get into the union side, and why do you want to go into possibly more hydronics versus just stay in a rack system, right, and low temp, and is it the CO2 changes issues, or because they're saying a pay cut, right? So it's not even like they're offering you more money, or maybe they're making the promise that it's less money now, more money later, which uh, then you get into the whole, well, we offer you all these benefits, and this is $20 an hour worth of benefits, and you're really making 60 something, 70 something an hour, but we're only actually paying your hourly wage. Like you get into this whole mishmash of just what is my opinion, marketing BS for hiring, right? It's just trying to convince you and sell you on this is worth your whatever. And it may not be. It's just part of their pitch to make you believe that it is, because it's in their interest to get you in the door, right? Anyway, yeah. Hopefully there's some shred of good information in there. And if there's not, I apologize. I tried. I tried. It's tough. Finally have time to join. Just hot installed a new liquid injection valve and strainer. Nice. Circuit on a vacuum. Yeah, and Jason, you made a comment about the Y deltas uh, on a video recently. I'm trying to remember which one it was. I think you were working on a. It wasn't an AW. I forget which one it was. Anyway, it was actually liquid injection valve. I don't think it's the same account. Either way, I saw you did a video where you were doing the oil service change on that screw that had the slide, and it was on a Y delta, and it just made me chuckle. Because you are right on some level, especially new machines. To see a new machine where the compressors are not, and we're also talking smaller systems here, where the compressors are not VFD driven, is just, you don't see those as much anymore. That's usually older machines, but it just makes me chuckle because it was very common to see Y delta, and to from my perspective, I think of it as, well, I still like, there's still a lot of Y delta out there, right? But to your point, some of that is just me glazing over the fact of, well, while there is still a lot of Y delta in the field, there is a whole bunch of variable speed in the field. And so, yeah, it was just a fun. It kind of made me one of those, just made me chuckle moments. By the way, if anybody doesn't know, Jason Johnson, he's got a great channel. He's still in the field. He's still showing and filming and doing stuff. He's got all kinds of fun projects and things he's got going on. So I would highly recommend, if anybody wants to see like active field content, you're not going to see that from me anymore. I've gone hardcore dedicated into the training side of this, right? This is my path forward. I've got all my like 7 years worth of videos I've made. You're welcome to go watch those. But if you want to see like new recurring field videos, I'd encourage you to go check out Jason. He's worth a look. Trying to catch up. No, it has nothing to do with CO2. I actually want to work on that stuff. Okay, so you want to get into hydronics. We have a lot of contracts with rundown stores. Okay, so you're with CoolSys. Yeah, I got you. So that's a pretty big company. I'm looking for more training. Everything I know, I've taught myself and would rather get with people that invest in their guys. I paused there because be careful with that, the whole invest in their team thing and training. Well, sure, you have to go through the apprenticeship on some level, or as far as I know, I don't know that you can even test out of the apprenticeship at this point, right? That maybe that comes back to the hall and just what they want to do, how much experience you have. I think at least in my area, I know some guys who have been able to do that. They went non-union to union and tested out of the apprenticeship and was able to go into their journeymanship pretty quickly into the process. I don't know all the details of how that worked out for them, but here's the feedback I've gotten. That's all I can share. Once you get into the journeyman phase of it, it is not, they don't do training on any scale different or better than what a good non-union company will do. Yeah, they're not any different on that scale. Now, maybe with CoolSys specifically, they're not putting enough time, or it sounds like they've definitely not put enough time into investing in you, in your training, your education, and putting you around people who also have the knowledge and experience to help train and teach you, right? That absolutely sounds true. It doesn't mean that same experience is going to be inside the union. Maybe it is. In your region, I will tell you, I've spoken with several companies who are in your region, and there is still a very strong journeyman environment there, where we've got really good senior guys still in the field helping train and develop in that specific region. That is not true in a lot of other regions, but several of the companies I've talked to that are in that specific region, including some of them being union shops, that is true. And union shops will, like, I've partnered with a lot of union shops. Okay, so there are lots of them who are very interested in training, very interested in technician development, and they will put that time and resource into it. Absolutely. And that specific region that you're in is one of them that I see the most positive feedback about. Your region and the West Coast, those two specifically, I probably see the most positive feedback about being in the union and how it helps. So I would just, this goes back to my internal biases and just experiences I've had throughout the process. It is very difficult to give you a non-biased answer. And so that's why you hear a lot of skepticism in my response. Okay, I call that skepticism out. That is where it's coming from. Yeah, and I don't want this to sound like a bash on unions in the process by anybody. Please don't take it that way. It's very much, I look at it from a standpoint of what is actually being provided, and there are a lot of people who disregard anybody who's not in a union. I've worked with many people that genuinely feel if you're not union, if you weren't trained by the union, you don't deserve to do this kind of mentality. So part of my issue with the bias is I go back to those having dealt with that early in my career, especially, it makes it very difficult for me because I have those people gave me very negative opinions I've had to learn to move past as best I can, and I'm still trying to. Um, it's not the union's fault that they responded that way, and they represented the union in that way. And not all the halls are like that. I'm just I'm not anti-union at that scale. I don't want it to come across that way. Anyway, yeah, 98% of the screws I've seen are VFD driven, but that's to be expected working. Yeah, well, and you also have to keep in mind, Jason, a lot of, especially in this region, a lot of the Daikin equipment is relatively new. Um, New enough that it was in the era when Daikin was going hardcore on variable speed. And so, yeah, it's not surprising to me that so much of what you do see, especially like being Daikin OEM, that it is variable speed given where we are. When you start getting into other regions and stuff and you start working on the McQuay versions and the older machines, you'll see a shit ton of XL and Y Delta stuff from older generations. It's just in our region, York and Train and Carrier just absolutely own this market for quite a long time. And Daikin is, I'd say, what, in the last 10 years or so, has made a really good push and has got a very strong local foundation here now. But again, that also puts it into that window where variable speed was just had already become the thing by that point, and Daikin was leaning really hard into that process. And so that's what I think about when I think about like that conversation and like probably why it feels or why it seems so much that way. Not trying to disregard it whatsoever. Like, you are right. There is a lot of variable speed. Train RTAC 134 suction. It's at 36 degrees. What could be caused? Low suction pressure. What checks should be run first? Let me see. Al-Mutarani. I hope I said that right. I'm sorry. Anyway, let me circle back to that question. Let's dive into our first official question. This comes from the portal inside of chilleracademy.com for the CQA Chiller Questions Answered portal. Excuse me for my sinuses. So if you have any questions, feel free to get them in there. And you can always, I upload the previous streams. There's comments we can get in and chat, have discussions, whatever the case may be inside of the Academy. So if you want to get your questions prioritized, that's the best place to put them. Now, we'll circle back. This is the only one I have for this stream. We'll circle back to the comment questions and we'll dive into that RTAC question here in just a moment. Could you please explain with your whiteboard how the condenser and evaporator on a Carrier 30 XWHP model heat pump would operate in terms of refrigerant flow to heat water at the condenser while simultaneously chilling water in the evaporator? Okay. So first things first, let's actually just kind of go back and look at the schematic provided on this machine. So these are the two that we have. I want to say up front, the manual for this machine, I'm not overly read up on this machine. I haven't worked on them. I haven't seen one in the field. So I'm going to go based off of just what I see in the design and from what I understand of the overall process of what we're trying to accomplish here. And I want to just call out Carrier on, if you look up the manual for this, it is ridiculous. They barely give you any descriptions. And there are, other than the, so this is a schematic for the dimensions, not a schematic for the actual machine, the circuitry, or anything else. This is just to give you dimensions and connection points. This is ridiculous. I really believe manufacturers should do a much better job on creating legitimate documentation that we can use in the field to help us. And this shouldn't be so restricted that they're only going to give their internal factory technicians proper access to this material. Now, if I'm wrong in this and somebody says, hey, if you go look over here, you can find that, please feel free to add that to the chat here or email me separately and I will apologize if need be. But from what I did find on this machine to answer this question, it's a joke. And I don't believe, this needs to stop. Anyway, we're going to go based off of what we see this design being. And something that I want to kind of point out here. Some of these machines that are being developed and being called heat pumps. So what they're designed to do, the evaporator and the condenser process, all of that remains relatively the same on the chiller from a fundamental level. What is changing is the operating temperatures we're trying to achieve. So with a normal chiller, we want to achieve a set leaving water set point of, say, 44, 45 degrees. And then our condenser water is going to be whatever it ends up being in the end, 80 degrees. And this is water cooled, right? Condenser water. So 80 degrees or, 90 degrees, whatever the case. Now, with a heat pump specifically, and let's just kind of talk about the heat pump circuit, then we'll dive into the machine a little bit. So we have our chill water piping. Let's see, multicolor. I don't have a different blue. We'll use this green, or we can use brown. Yeah. So we have our chill water piping. Okay. What I've seen of these systems, when you've got a heat pump specific unit on these water cooled specifically, they don't have like a reversing valve from what I've seen. What we'll have is, you will usually see, this is just what I've seen so far, a primary chiller. Okay. And then we'll have our chill water loop. Then we will have our heating loop separately. Okay. So we'll have heating loop, and we will have our boiler down here. What ends up happening is, here in the middle, we'll have the heat pump chiller. And how this all ties together in the end. Now, I'm still learning about this myself, because this is a fairly new concept to us in the chiller world. We've had heat recovery for a long time, but actually a heat pump system ends up being a little different. So we still have the primary sources here, but on some level, this heat pump chiller, what we want to do is basically use it as some form of heat recovery system, where it can contribute to the cooling load and reduces load on the primary chiller, and then it can also contribute to the heating load and reduces load on the boiler. And that is the whole concept of why this makes sense from what I've seen of the industry. And so what ends up happening is the hot water or the condenser water piping will be connected here into the hot water loop, and the chill water piping will come across, and this would be our leaving chilled water. This is our return or entering chilled water. Just kind of give you an idea. Okay. And essentially, we're bringing the water in, we're processing some of the load, contributing it back to the primary loop, and then allowing that to process through. And it takes some of the heat that this chiller would have had to just send to a cooling tower or reject to an air-cooled facility, right? It takes some of the heat that this would have had to do, and this, say 55-degree water or 50-degree water, by the time we're taking some of the GPM, rerouting it to add to where the heat pump is then taking some of those BTUs and not the primary chiller, right? So that's the overall process of what we're looking at. So when it comes to the question of how we're simultaneously heating and cooling, this is what I see as being discussed as an industry standard. Now, there are other variations of this. This is not like the set primary, but this is one of the main recommended ways that I'm seeing this pushed right now. There are other configurations, okay? I'm just saying that up front. If you research this or look into it, you will see this done in a few different ways. This is just a more prevalent one, and this is the one I'll focus on, is to explain the simultaneous aspect of this. So these chillers are, from what I've seen, usually not replacing the primary cooling system. It's not replacing the primary heating system. It's usually installed as a supplemental so that we can just literally transfer heat out of here into here. It's a type of heat recovery setup. Truly. It's just, we're calling it a heat pump for whatever. I'm honestly, why call this a heat pump versus heat recovery? In my brain, I think of this as heat recovery, but that's just the way I think about it. Either way, that's what we're doing. So what makes this chiller different from this one? Well, this one is designed to maintain a set leaving water temperature, and it's going to have a lower condenser water temperature compared to what we expect here, because on the condenser side here, like, we're talking 120, 140 degrees contributing to this hot water loop. So that's not where we want to operate our primary. That's very inefficient, and that's not necessary for our primary cooling system. But these heat pump chillers are designed to run at really high leaving water temperatures. And they're also designed to take in hot water temperatures, because you got to think, if we've got, say, 140 going out, it may be 100 to 110 coming back in. So we're feeding 100-something degrees water into the condenser of this heat pump and trying to produce back out, that 120 to 140 degrees on the other side of it. And that's where these are designed to handle those hot water temperatures while also being able to manage the chill water cooling, because we do still want to achieve a 45 degree leaving water here, or whatever the set point is the facility needs. We still want to achieve this, but we also want to be able to contribute actual hot water to a heating loop. And so it changes how we're going to design this, what the tonnages are. Our lift and our compression ratio is significantly higher by design on a system like this in a completely different way than this would be. Hopefully that helps. This is a very important aspect to understand in terms of what we're seeing with the heat pump chiller market in this particular application. Again, there's other configurations that you will see, but this paints a picture as to what is being achieved and what we're discussing when we say simultaneous heat and cool. Here's your primary cooling. This is your heat pump unit, moving the heat from one loop to the other. We still have a primary heating source of some kind. So when we scale that back over to the schematic here, now let's actually just look at this machine in its entirety. It's very similar to the old school screws we've always been used to with these carriers. They're not that different. There are a few modifications that I see here, but we've got our condenser down here. We've got our evaporator up here. I know this is the evaporator because my suction line is coming off of this top barrel into the compressor. Our control cabinet is right here. Right? We can see we have a braze plate economizer. This is where I have no experience with this machine, but I know our components. I know what these things are meant to do independent, and it does not matter how the manufacturer implements these components. If I understand the core premise of what they're intended to do, then I can understand how to make sense of what this machine is doing to work and function correctly. This is where my certification course, like this is why it's built the way it is. I'm teaching you each of these little individual pieces so that it doesn't matter how all this is put together. You can look at it and you understand. Okay, suction line comes off of the evaporator. This would be a discharge line here and here. And if we come over here, we can see that on this side, we come off, we have a muffler into a T, or call it a header, doesn't matter. We have isolation valve. They're just ball valves, and that feeds into our condenser. So we know immediately evaporator, condenser. Now, if we were to walk up to this machine, we would likely see that this top one is insulated, the bottom one is likely not. That would also be another obvious giveaway, but just from a schematic alone, just from this, we can determine which is which, just based off of our piping. So, suction comes up, we push into the discharge on the other side. We'll actually start over here with just the basic cycle, then we can discuss the economizer. So we come out the discharge, we go through the muffler. So this muffler's job is to help smooth out the refrigerant flow, take some of the noise, take some of the pulsation that happens from just the compression process. And then this feeds into our header here. So this splits, feeds into either side of our condenser. Our liquid line is here at the bottom. We can see that drop leg there. And so this just helps create the circulation turbulence internally here, so we have an efficient condensing process. And this machine doesn't have an oil separator, right? We'll get into, we have an eductor instead. That's what this is right here. So we have an eductor system that is acting as our oil separator in this process. So it looks like they're expecting the oil to collect here at the bottom of the condenser, and I don't see a line coming off the evaporator. Anyway, we'll circle back around to that. Coming out the discharge into the condenser, processing through the condenser, back out this bottom drop leg, and that feeds up into our economizer, which then out the economizer, this is our insulated suction line. We can see the EXV right here at this angle in the schematic. This is our metering device for this particular machine, right? You can just barely make it out there just behind these relief ports. So this right here is a double stack relief coming off of a service valve. So just behind these two reliefs, you can see the economizer. So there's the EXV for the braze plate and the economizer circuit. There's the EXV for the actual evaporator. So that feeds up to this insulated line, ejects into the bottom. Now, for right there, I know that this is a flooded style evaporator because the pipe is connecting into the bottom, and it will fill the bottom through a distribution rail inside the evaporator, and then we'll maintain a liquid refrigerant level above the tubes. On this particular style, you're probably looking at 1/3 to half of the evaporator is going to be a tube bundle that we need to completely submerge the majority of it in that liquid refrigerant, and then that will pull back up into our compressor. This is what I think they call them Paragon screws by Carlisle with Carrier. So this is part of your slide assembly for the slide valve in here on this is a screw compressor. You can tell by the design and the layout of it, this is going to be a water-cooled screw, right? So we can see all of that just based off of this dimensions schematic alone. This is just what they provide so you can see what the dimensions are. Now, there are two boxes down here. There's one here and one here. To be frank, I haven't read it deep enough into the manual to try to figure out what these are, and I'm not familiar with what these boxes are. So that would be something that I'd have to look up and try to see how that's contributing. I can assume it's probably part of the oil management side of the system. That would be my assumption, but I don't actually know. And I do know that this is a little pipe here and a pipe here that connects into the bottom of the condenser. Again, this would be something I'd have to dive into of what are these serving in this process. Maybe that has something to do with, hey, we're running really high condenser pressures and condenser water temperatures with this machine because it's a water-cooled heat pump. Or not but water cooled, because it is a heat pump system. So that might have something to do with it. Again, we'll come back to that. So if we come back to this other side, we can see the liquid line leaving the bottom of the condenser here. We can see these same little chambers. At one time, I would have guessed that these were like seismic isolators of some kind, but I don't think that's what these are actually doing. Anyway, liquid line comes out. We have another isolation valve. I will say this, I really appreciate all the different isolations. Makes it much easier to service a machine like this. Anyway, come up into our filter dryer, right? So this is probably a 2 cartridge dryer, looking at the size of it, unless they did one of their screen things where it's partially dryer, partially screen. So maybe just 1 core in there. It's a 1 or 2 core dryer. Here's the plate to open it. This is your inlet, outlet. So we come out of our filter dryer up into the top of the brace plate. We cycle through the brace plate and we come out on the back side, but not this upright EXV, but there's another one back here that we could see from the other side or the other angle that's coming out that pipe through that EXV and then out this insulated line into the evaporator. So that's the basic refrigerant circuit. The economizer circuit, we can see there's a pipe here. This pipe comes down, feeds into this smaller EXV. This EXV then provides a medium pressure liquid refrigerant that's going to help subcool the primary liquid refrigerant down further. So we're going to increase our subcooling, which helps get our enthalpy lower on that liquid refrigerant. And then this is going to flash off out of the evaporator and up into this. I'm assuming this is a style of accumulator. Looking at this would be my assumption. So this is our economizer suction line coming back into the compressor. We're going to feed into a medium pressure port here at the compressor. So this pressure here is usually not down at a evaporator saturation level. This is like a medium pressure saturation, typically feeding into the compressor usually. And so I would assume that because we could have such extreme temperature swings with this system, that maybe they put this accumulator in here in order to protect the compressor from any possible slugging, because once we come out of this tube and we go straight into the screw bolts, and if we don't do something to mitigate, possible floodback issues, this is not something you see on all systems that have a economizer line like this. This is one of the few I've seen that actually have an accumulator implemented. And then again, that is my assumption. This is an accumulator. If the manual is worth anything, it might explain that to me. Anyway, so yeah, we come through there, economizer port into the compressor. All that compresses, comes back out the discharge. That is our basic cycle here. We have a standard, call it water-cooled condenser with our discharge lines coming in. We have a flooded evaporator. All those components, all that process is going to function just the same, just like we would expect it to at any other point. Like I said, the only thing in that circuit that I don't recognize is going to be the those little boxes down at the bottom of the condenser. I'd have to do some research to see, okay, what are those? What is their purpose? That's not something I'm familiar with. But beyond that, it's a basic, it's still the same chiller in the end. It's doing all the same things. It's just designed to operate at a much higher compression ratio, much higher condenser water temperatures in order to achieve the heat pump functionality. That is its ultimate baseline goal. And in that process, we reduce the load and we allow the primary cooling system to unload some, because it's not having to process the entire load on its own. And that's one reason why it's recommended that they configure these to have to run chill water on the evaporator and not try to pipe in through the condenser water, because one, a lot of these systems run open loop condenser. So that's a lot of trash that you could potentially be pulling into the chiller trying to run on the open loop side of the condenser. In addition to that, at that point, you're taking some load off of the cooling tower, but you're not taking any load off of the primary cooling system. So in order to achieve better efficiency, we can come back to this here. So to achieve better efficiency, if we were piped in over here, while we remove load from the tower, we're not helping this chiller at all. Whereas if we can pull some load off of this chiller, then we, by default, also pull load off of the cooling tower, because now we're not having to move as much heat into the condenser water, hence the cooling tower has to work less. So by pulling it off of the chill water loop, the cause and effect would be this entire side of the circuit, or of the system, gets to unload a bit, because it has just less heat being pushed to it, and it's being just rerouted for the hot water circuit. So that is our basic high level of what this specific machine, how it's configured, how that refrigerant circuit, how I would expect it to operate. And like most of what I'd be troubleshooting is going to be relatively similar to any other troubleshooting I would do, except for the fact that I would keep in mind the elevated condenser head pressures and water temperatures. That's going to be the primary difference for this machine compared to other styles of chill water systems. Excellent question. And yeah, Carrier, do a better job, please. We don't appreciate. Just go look up the manual, right? Y'all go look up the manual for these and breeze through that handful of pages. No. And I gotta say, Carrier is actually one of the companies, or is, that I feel like does really decent manuals. Like, sure, they've got a lot of typos and stuff scattered throughout them, but I've always known Carrier to like have a really solid manual. And so it was very disappointing, reading up on that machine to answer the question here, just how I'm just very frustrated with with how they manage that. That's all. And you're getting to deal with my frustration. How about that? Okay, so I'm going to try this again. Al-Mutari. We have an RTAC. What could be cause? I see Jason, I think, responded. Wall separator. Like others are. See the reverse. Sorry, I'm reading through the comments here. The heat pump, air cold chiller. Yeah, Daikin's air cooled heat pump does not look like a machine I really care to work on. Yeah, RTC liquid level sensor. I would start with verification. Yes. Okay, let's pull this question in here and discuss it. All right. Trane RTAC R134A. Suction pressure is 31 psi. Evaporator saturation is relatively 36 degrees Fahrenheit. What could cause low suction pressure, and what checks should we run first? So starting off with GPM, that'd be a big one. So we have a low suction pressure. So we want to, first we need to verify GPM on evap. So this is an air-cooled machine. RTAC is an air-cooled screw produced by Trane. It's one of their newer screws. I guess it replaced the RTAA series. It was a great machine. Still is. I'm a big fan of the RTAC. It's been replaced now by the RTAF. Replaces the RTAC in new machines. So you're not going to see new RTAEs or RTACs out there. But anyway, so GPM is first thing we need to verify. And while low GPM is one of the more common causes, don't just go with low GPM. There's been plenty of plants where I've seen that the pumps were oversized and they were pushing water so fast, so hard through the machine. We had this crazy high pressure differential, and it wasn't because the evaporator was plugged or anything. It was because the GPM it had so much force on the evaporator, was moving too quickly through it. In that scenario, what ends up happening, the compressor has to load up really high in order to try to get that leaving water down, and that water is not in the evaporator long enough to be cooled properly. So then we have to really drop our suction saturation in order to try to get enough heat out of the water to make set point. So what ends up happening is we start running into low suction pressure issues because we have a really high GPM. Now, those aren't that common, but it's something to just remember. It does happen. So don't just assume if it's not low GPM, then we're good. Make sure that we're not too high on that GPM as well. It could also be a charge issue, all right? So these machines, I believe, run, what is it, around 12 degrees or so of subcooling at load. So that would be something to check, is what is your subcooling that you're running with a load on the machine. And you should, that'll help give you an indication if you are seeing low suction pressures, but you've also got a really low subcooling. That could be a very quick indication, okay, we may have a charge issue here. If your subcooling is good or high, then it may not be charge. It could be dryer or metering device. So I'm going to say MD for metering device or dryer issue. Okay, so and you'll see this. You'll have really good subcooling, but the suction pressure is just not jiving. It could be a transducer issue or a sensor issue. We're just going to go sensor. So if a sensor is not reading correctly, then Senor. That's not how that's spelled. Sensor. If there's an issue with a transducer, temperature sensor, something like that, it could be causing it to starve the evaporator, or the evaporator may be perfectly fine, and the sensor is just telling you it's got a low suction pressure when it really doesn't. So that could be a transducer issue at that point. We could also have a liquid level sensor issue. I'll separate this one. So what I mean by this is like temperature, pressure. So say TP in parentheses. This could be a liquid level. Lipid level. Okay. Liquid level sensor. Add the S this time. If this is either out of calibration or just flat bad, right? So we've got a bad liquid level sensor that could be causing it could be forcing the refrigerant level down and causing a low suction pressure trip, or just a condition where maybe you're suction limiting. If this level sensor is not reading correctly, it's not going to open the metering device correctly. So this comes back to evaluating whether it's charge or issue or not, right? So that's one of the early areas. Get our flow right, make sure our charge is good. If we have a good charge and we have a load, I stress the load part because if we have a really low load condition, you might see low subcooling at that state, right? If that is true, don't just assume it's a charge issue. It could just be a load problem. But if you have load and the GPM is good, then we're going to come back to one of these other conditions. It's not likely a charge problem. It's probably a sensor or maybe the metering device, something along those lines are far more likely to be true. Yeah, I would say these are the main things I would want to be looking at. Maybe the machine is getting stuck in a loaded position. Okay, so is the compressor unloading? We'll say compressor stuck. Okay, so there's a slide valve in that compressor. Is that compressor able to unload itself? Do you see the RLA fluctuating? Is it coming down to make leaving water set point? Thing is, if you're seeing this, what you will likely see is the leaving water is also going to be lower than set point significantly, and you're not going to see the compressor backing off. You also, depending on where it gets stuck, you may have issues where on occasion, every once in a while, it trips on a motor overcurrent or something like that at startup. You could have something along those lines. That could be another indication that the slide valve is not working correctly. And if the slide valve is stuck in a loaded position, then that could cause a low suction pressure to show up as the machine gets the loop load down. So this will be a result of over processing the loop, that forcing our saturation down heavily. That could be part of our issue. Other than GPM, though, we could have a dirty evaporator. So a dirty evap. This is an old enough machine, being an RTAC, that we could just have junk, silt, whatever, in the evaporator. And so you may not have a GPM issue, you just can't make heat exchange. That's another thing to consider. Those machines, they have an oil separator, so we shouldn't be stacking oil in the evaporator. I think those also have an eductor, if memory serves. I'd have to pull the manual. I'm trying to think. Why don't we do that real quick? Do these machines have an eductor? Let's go look. Let's draw this. Not draw, but pull the manual. Let's go train. Where is it at? Should be this one. Nope, not that one. Not that one. What the hell? Here we go. Yeah, this is the one. Okay, so I'm going to browse through here. What I'm looking for is the refrigerant schematic. That's the water connections. I'm pretty confident this machine has a separator. Here we go. There's the compressor. Yes, okay. So we have right there. So number 11 here should be our oil separator. We can check that. Yeah, oil separator. But there should be, I think there's an eductor. Is that right? What is number 4? Evaporator oil return line. Yep, and filter. So there's a type of eductor system on this system. So that could be another potential problem. What could happen, and just looking at this as our example, some amount of oil does make it past the oil separator. So it's not 100% of the oil gets captured. When that happens on this is a flooded style evaporator. The oil is going to collect in here. Actually, I say these are flooded. These are falling film because the EXVs on these feed into the top side of the evaporator. These do not feed into the bottom. So because the two-phase line and the metering device feed into the top, that's an immediate giveaway of a get that a little closer. Immediate giveaway of a falling film style, which means they run a much lower liquid level. They don't stack, they don't stack a lot of refrigerant in the bottom. It's going to be very minimal. That being said, you'll see that it is very specific that oil return line comes off of the bottom of the evaporator down here. And I do think that is correct. There is a line that comes right off the bottom, and that's because we just have such a low liquid level in here. So the very bottom of this evaporator is where that oil is going to stack. So if this oil was allowed to stack or got in here too concentrated, if you had a really high oil charge, right, that high oil charge could make it to where the refrigerant is getting past the separator at a higher rate. The separator is not able to process all of that back out of it, and then it gets caught into the evaporator. That heavy oil charge will also cause low suction pressures, and you're going to see that through the approach values. So several of these conditions, what you're going to see high approach values if we have a low charge condition or an underfeeding of the evaporator of any kind, or a dirty evaporator. All of those are going to cause high approach conditions, which I would expect the approach on this machine to be less than 3 degrees. So approach being the difference between suction saturation and leaving water temperature. The difference between those two temperatures on this machine should be less than 3 degrees. If it's more than that, then that indicates a heat exchange issue, which then plays into charge or underfeeding of the evaporator in some way. So that's everything I would want to be looking at, checking for, and trying to test if I am having a low suction pressure condition, and pretty well in that order. That is the order I would probably go in from top to bottom of possible issues that I think I might run into. I think that's a reasonable list of, okay, I'm going to, my very first place I'm going to start is going to be, what's my water flow? All right, here's that. Okay, how much load do I have? Where's my subcooling? Yada, yada, yada. This is going to be the stepping process that I'm going to put myself through to try to verify, okay, what is our actual problem? What is our diagnosis on this machine? Let's see. Between DX, I think I had one other error. Yeah. I've got a weird chiller I work on. I'm in the PNW low ambient AHU chiller. So, yeah, screw compressor. No, STRC. I'm not familiar with what you're describing there. No. Maybe if I had a little more details, that might kind of trigger something. But from what you've explained, it didn't like kick anything off in my brain. You're always late, Sterling. I've come to expect it there, Bubba. It's all right, man. Good to see you. Good to see you too there, Barry. Let's see. I have a heat pump. Yeah, so can you explain the difference between DX cooling and air-cooled chiller? Yeah, absolutely. Okay, I see your question. It's a very fair question. And this question does come back to the premise of, like, this starts off with like literally lesson number 1 of the certification course. Here, let me make that a little easier to Back. There. That should be much easier to read. Okay. Can you explain the difference between DX cooling and air-cooled chiller? Let's do it. Let's start off with what is a chiller, right? Clearly, lesson number 1 in my certification course. What is a chiller? And I want to see some guys take a crack at this. So, how in the comments, how do you define that? Define what is a chiller. What is the separation of a chiller from anything else we work on? What definitions do we have? I want to see it. Anybody got anything? You don't have to be right. Like it's one of those questions where, see here, this gets into a core fundamental of so much understanding, and this is a question that I've never had asked in my life until it just occurred to me. I was trying to explain this and like building the academy, and it literally comes back to, how do you define that? What is that? Okay, water cooling. All right, so we're cooling water at all. How you doing there, Carlos? I see you there, bud. That is a good answer, right? So water cooling is a good answer. Do we have a more detailed answer? Or is that just completely, like, how else would you say it? Chiller's life goal is to cool water down. Yep. So both of you, absolutely on point. A chiller has a hydronic evaporator. Hydronic evap. That is the core premise of everything that a chiller has. So a DX system. Now, what do we say when we say DX? We're saying direct expansion. Expand. That's close enough. We're saying a direct expansion system. So this, instead of being hydronic, is an air over coil. It's air over. Now, the question was, with an air-cooled chiller, right? So now we're talking about the difference of, okay, we've basically got two rooftop systems. One makes chilled water, one cools the air. We have a DX system and an air-cooled DX system and a air-cooled hydronic system. They're both air-cooled. See, the DX units we have, they're also air-cooled. There are systems out there that have DX evaporators, but are water-cooled condenser. We call those water-cooled heat pumps in little small office buildings many times. That's a DX unit with a water-cooled condenser. It's DX because we're having a coil that does direct expansion in the coil to the airstream. Hence, we refer to it as a DX, a direct expansion. A chiller, we don't have our refrigerant having a direct expansion process on the load itself in the airstream or in the coil or anything like that. Instead, our evaporator is processing water or some fluid. Maybe it's not even water. There are some cases in processing facilities we're not processing necessarily water, but we are processing a fluid. And that fluid is going through a hydronic evaporator. So the refrigerant stays localized to the machine, but so does an RTU, right? Now, a split system, sure, we send that refrigerant out elsewhere. So there's a lot of similarities here. And here's a big thing. If you can make the connection between an air-cooled chiller and a RTU, just a standard rooftop unit, If you can make this connection back and forth in your mind, you suddenly understand chillers way more than you think you do. GPM equals CFM. There's the difference. It's just converting one to the other in your mind. The troubleshooting we go through, the conditions we will see, why we're going to test things a certain way, so much of that process stays the same. So much of it. It's just we're trading, instead of cubic feet per minute, it's gallons per minute. Instead of a vapor that we're moving through with a blower, we have a, and what's funny about this, a centrifugal blower motor, right? It's still centrifugal versus a centrifugal water pump moving a fluid, of a liquid fluid at GPMs. That's all we're discussing here. Now, I'm not trying to negate the fact that there is a lot of very specific knowledge to oil circuits. We have screw compressors. You don't see, they do exist, but you don't see very many screw DX systems. The ones that I've personally worked on are all built up systems, meaning they were site designed specific. They're not just some universal package you buy and have shipped to you. No, this was designed by a team for that specific site. But they still exist. You can get DX screw systems, or you can have one made or built. The point is, though, like, it gets more complicated, right? There is things about, we wouldn't expect to see screws in a RTU system, like a package unit on the roof. We wouldn't expect that, even at 300 and 400 ton RTUs with 25 ton scroll compressors in them. Again, they're scroll, so that changes how that machine's going to function, how it's going to control capacity, things of that nature. But everything else ends up staying cross-compatible in terms of how we would troubleshoot the process. But that's all this comes down to. A chiller is going to have water going through the evaporator. A DX RTU is going to have air going across the evaporator. That's it. Really take some time to think about these. I encourage you to try to do that. How would you troubleshoot a low pressure issue on an RTU? What's one of the first places you would go to look at if your evaporator was tripping on low suction pressure? Me? I'm going to go check the blower motor. Did it throw a belt? Is the fan spinning? Did trash get into the fan? What's my static pressure I'm running at? That's what I want to see. Okay, translate that exact same troubleshoot into GPM. You tripped low suction pressure. What's my pump doing? Is it running? Do I have pressure? What's my differential pressure across my evaporator? It's no different than taking differential static pressure across an evaporator. Like, so much of those concepts are translatable right back and forth between them. Anyway, that is my answer to the question of explaining the difference between a DX and an air-cooled. It comes down to that on just a pure fundamental scale. Hopefully I didn't get too off in the weeds in that question. If I need to spend a little more time getting into the nuances of the technical aspect, I can. But yeah, I'm assuming that you've got some level of basic training with that answer. I'm not getting into like all the crazy nitty gritties there. Because basically, okay, what are we doing with that chilled water? We've taken that chilled water and we're putting it through typically in a comfort cooling scenario. We're not talking about industrial. So in a comfort cooling scenario, we're taking that chilled water, we're putting it through an air handler that is then having air move over that coil and putting heat into the water, and the water carries the heat back to the chiller. Whereas with a DX system, we're just having that water pass directly over that refrigerant, or that air, the air pass directly over that refrigerant. So yeah, I could spend a lot of time just kind of diving into that. I don't know that we need to. Starling, things have been busy. I'm looking forward to the Houston class though. Like we've still got a couple of seats left. If somebody is wanting to jump in last minute, like I would get everything set up this week. I'm gonna have to be closing enrollment. To do that, you just reach out, send me an email at hvactime@hvactimetx.com. Send me an email there. I can just tell me how many guys you're wanting in, and I've had several technicians take that, go straight to their manager. Manager says yes. I'm able to just I'll invoice you. That's how the process works. I'll just send you an invoice. It's got an online payment option. You can just pay the invoice that way, book your trip, be there, ready to go on class. We're going to be doing hands-on with the compressors themselves. I've got a turbo core. We're going to be doing this in Houston at a screw remanufacturing shop. So we're going to see like these compressors. We're going to actually be able to put hands on them, do some meg checks, talk about how these machines work, how we're going to troubleshoot them. We're going to go through a whole variety of different troubleshooting scenarios that we may run into, and having an understanding of how we're going to approach that in the field. And we're going to spend a couple of days going over recovery practices and actually hooking machines up and moving refrigerant. I've partnered with AGAS and Navic. They're going to be supplying a bunch of equipment for setting up multiple stations and learning how to do all this stuff that are things we should be doing routinely if you're doing field service on this equipment. So just if you're interested in that, send me an email. I've only got a few seats left open, but if you want to get in on that, like you need to book everything this week. Just throwing that out there. I'm really excited about this class. It's gonna be fun. All right. Could you explain a situation, screw chiller with too low suction pressure working in a plant, but normal discharge pressure? The charge is okay. So Nader, or Nader, maybe it's Nader. Knowing the charge is okay. I mean, situation is screw chiller, low suction pressure. Yeah, so that goes back into a previous question very heavily, where we talked about, now it was very specific to an RTAC, the prior question, very specific to that, but I've got some thoughts on this. I will just kind of talk through this for a moment. Just give me 1 second. Could you explain a situation of screw chiller with too low suction pressure working in a chiller plant, but with normal discharge pressure, knowing the charge is okay and the DX evap is clean and new? All right. Well, first I would question, what is too low? Like, what are you calling too low? And if you have a DX evaporator, I'm going to immediately assume then you have a shell and tube DX, which means that even if it's a braze plate, either way, it means you have a higher approach than you would normally see with a flooded style of evaporator. So with a DX style evaporator, where the refrigerant is in the tubes and the water is on the outside of the tubes, it's very normal to see approach values of 8 to 10 degrees. It's very normal, especially specifically with a full load on the machine. All right, so that means if it's designed for 10 degree difference between entering water and leaving water, then if you've got 7-8 degrees or more, you've got a full load for that machine. That machine should be able to really stretch its legs and open up, and you're going to see those higher approach values. So I think first we need to make sure we're defining what is too low of a suction pressure in the first place. That also comes back to, what is your leaving water temperature? I see this a lot where facilities want to run 40, 42 degrees of leaving water temperature. That's fine if that's what the facility needs, but depending on the style of evaporator you have, if you've got a DX style evaporator and you're trying to run a 40 degree leaving water temperature, well, water freezes at 32. Most chillers will have a suction limiting set for about 34, 35 degrees of saturation. Maybe I should draw this or write this out. That might help. Let's give a visual to this. So if we have, okay, you got another response. So shell and tube DX evap, suction pressure is 10 psig and approach is 20. Okay. That gives us some really good details there. All right, so 20 degree approach. We have a really high approach. So you said 10 psig. So I'm going to pull up my ref tool by Danfoss, and I'm curious. So I'm assuming we're 134A. We don't specify. Yeah, I'm going to assume we're 134. And I'm going to go with a... and this is a great troubleshooting conversation. So if we want to just start kind of feeding us info, like the more information we have, the better we can give you. Okay, so reading this, if you've got a 20 degree approach and you're at 10 psig on the barrel, assuming it's a 134A machine, that gives us a saturation of, basically, we'll call it 7 degrees. Yeah, it is 134. Perfect. So our current saturation is 7 degrees. Here, let's do this. It's a screw with a ST shell and tube DX 134A. That way everybody can look at this. We're all on the same page. We've got a saturation of 7 degrees Fahrenheit. And you say an approach of 20. So that would mean that your leaving water is, we'll just do LWT. leaving water temp would be 27 degrees. So you've got a glycol based system, I'm assuming. Right? So if I'm reading this right, and this is where I need you to give me some feedback and tell me where I'm wrong or if I need more information here. This is really good, by the way. I love doing these. These are really fun kind of puzzles to put together. So we know we have a shell and tube DX 134, 7 degrees. So you said 10 psi is our evaporator pressure, which means our saturation is 7. That's what I actually care about, is the saturation. I'm not too worried about the physical pressure. Our approach, you said, is 20, which would mean that if we're running the math right, so to get the approach, we have to subtract our leaving water, or we have to subtract our saturation from our leaving water. Hang on, I'm screwing myself up. Yeah, leaving water minus saturation gives us our evaporator approach. Getting twisted up here. The difference between those is 20. That's how we should be getting approach. So one thing is that how you're calculating the approach? Are you subtracting saturation from leaving water, the difference being 20? If you're running a 27 degree leaving water temperature, then you're going to have a glycol loop. If you have a glycol loop, you're going to be running a higher approach naturally anyway, depending on your concentration. So this is really important. Like we have to understand this if we're going to define too low, right? So what leaving water temperature are we wanting? That's one question. So what is your leaving water set point? Would be one piece of information. And if this is not your leaving water temperature, then I need to know what is your leaving water temperature at that 10 psi. Because at that point we need to recalculate the approach, because given these numbers, like this is what you should be seeing happening. And I do apologize, everybody. There is a little bit of a delay versus what I'm saying and as I'm saying it to kind of how the comment feeds update. So I know that as he's trying to respond and give us some more information, there's going to be a pretty serious lag between him hearing what I'm saying and then him being able to reply to what I'm saying. So I do appreciate the patience there. Okay, so leaving water set point is 45. So are you telling me that your set point is 45, but you're actually getting down to 27 leaving? Is that true? Or are you seeing 10 psig at 45 degrees leaving? This is a really important piece of information we've got to get right. Like, we need to be on the same page here. This completely changes how we're going to approach this troubleshoot and what we're going to do for this machine. Let's go back and review this real quick. Low suction pressure. Yeah, my whole point I was going to make on the... Oh, here we go. Most of the time works with 20 psig, but sometimes goes to 10 psig. Okay, it's very important. I do need confirmation on when you're seeing those pressures, what is the actual leaving water? Is it at set point? Right? I do need so assume 20 psi. Okay, so let's update that saturation to 20. Okay, so 22 psi or 22 degrees. So the normal is getting down to 20 psig, which gives us a 22 degree saturation. So if we update that 20, so that puts us at what, 42? If our approach is 20, So that, again, that takes me back to, that gives you a leaving water of 42. This would tell me a low load. And if we're discussing a leaving water of 45 at 22 degrees of saturation, then that would make our approach 23. A little above set point. Okay, all right. This is really good. No, I'm not, and by no means, please don't take any offense to any of the questions. This is part of the process. We just have to work through it. So let's just assume, so you say a little above set point, so it could be 45.5 or something, right? So we're just going to assume a flat 45 for simplicity. It's close enough. There's no need to get into tenths of a degree in this scenario, which makes our approach 23. And I see your point of, you were probably rounding with your approach. So you were just saying 20. I'm very technical, right? So I will nitpick things to some degree. Just bear that in mind. So to me, 20 to 23 could be the difference of a diagnosis, the way I see it. Now you can make the same argument of, okay, well, a tenth of a degree. Anyway, yeah, so some of the guys are kind of getting on a similar page here, where we're thinking possible low water flow. So let's think through that. So if we have a low water flow, the issue with low water flow is we have a really high approach value. Have you checked your DP across your evaporator? Do you know what your pressure difference on the water side specifically is on the evaporator? Let's just kind of take in what he's saying. So let's, saturation at 22. Charge we know is good. We've got a clean evaporator. It's a screw machine. So yeah, right now, my immediate thoughts, just from what we do have, could this be because of low delta syndrome as it works? Yes, absolutely. So if you've, this gets back to, so GPM and load management. Any machine, when you start getting down below, so DP is normal, okay? When you start getting down below a temperature difference between entering and leaving water of, it depends on the machine, but at many of them, 3 degrees, like as soon as you hit 3 degrees or less, a lot of chillers will really start to struggle. And you can have weird saturation issues, right? Can pop up. My gut, just from what you've given us so far, my instincts lean away from that. Because if it was a low load, see, here's the thing. If it was a low load issue and we don't have enough heat coming into the chiller, we should not be at this high of a leaving water temperature. You said we're right at or just above set point. That wouldn't be true. We would see this leaving water temperature much lower. And we would get down closer to the possible trip point for that leaving water. Okay, so we may trip at say it may do a shutdown. When I say trip, I mean shutdown specifically. We may shut down the chiller at 2 to 3 degrees below set point. That's not what we're seeing here, but that's what you would expect to see with a low load. What we're seeing here is we are maintaining our set point temperature relatively, but we've got a really low saturation. You say DP is normal, and I was already thinking, my gut doesn't say GPM issue here. I would not expect GPM because now it is possible, right? There are a scenario if we had like barely any water moving through this machine, you could see readings like this, but I don't think that's true. So what I'm wondering is, are we oil stacking? Okay, so this would go back to the adductor circuit. We have a screw. Wait, no, what am I saying? Well, this could still be true. All right, let me get my head straight here. One of the things that can happen with a DX evaporator, especially if we have a low load, so the compressor is not able to stage up properly and is running at a minimum load. What that also does is it lowers the total velocity through the machine. And by velocity, I mean refrigerant velocity. So part of what can happen, let's see. Let's say this is our evaporator. And then our tubes here. We have our refrigerant entering here at the bottom. We're going to come up through the evaporator, and then we're going to come out the suction on the top of it. So this would be a standard shell and tube DX design. Metering device would be right here. Okay. What can happen when we run really low loads for an extended period of time? This could be it could be as little as just a few hours worth of runtime at very minimal loads, and our compressor itself is just barely even staying on. Then what can happen is these elevation points right here where we make turns and we have to work our way up, like vertically up in the circuit. Our refrigerant is moving so slowly that it's not able to get enough velocity on it to move that oil. And what happens is that oil slowly starts to accumulate at all these little low spots where we need to vertically make that oil rise. And part of what you'll see is in this process, the oil separator, or not all of them have sight glasses on them, but if yours does, you'll see the oil separator levels begin to lower. That's if you can see that. In that scenario, with enough runtime, you can oil log this evaporator. The fix for this is to either increase head pressure even further, so turn off some condenser fans, force a higher velocity, or let that circuit, the best thing to do is let it stage up. And so if this machine is running at minimal load alongside several others simultaneously, I think you said there's five other chillers potentially online. I'm assuming you mean 5 others online at the same time. When you start to get into those conditions, and this is something that doesn't get managed at the chiller, it gets managed at the automation level, the other plant controls. When you start to have the load decrease across all those chillers, it is best to start to unload some of those so that the other ones can get more load on them, because there is a breakover point where it's detrimental to run too low of a load for an extended period of time on these machines. So this could be one issue potentially that you're seeing on that particular circuit. I'm assuming this is for a specific circuit. Maybe you've only got enough load to run one compressor on this machine. That's my assumption, right? And so this could be one. I did see, who is it, Sterling said air trapped. That's another very good possibility. So on the top of the evaporator, there's almost always some little taps, right? And they'll usually come from the factory with a plug, right? So it'll be just a threaded plug going into a pressure tap that accesses the water side. What can happen is air can get trapped up in the top of that evaporator, and it won't actually work its way out of the evaporator. And to Sanchez's point, depending on where that evaporator is in the circuit, it may only affect one of the chillers. Okay, so this air trapping could be isolated to one specific machine depending on where it is at on the header assembly and how it's all piped in. All that plays a difference into where does that air go and how does it get stuck there. So my preference is, if I'm thinking this is the case, isolate the water side on that evaporator and then open or remove one of these plugs, at least one of them, and I like to either put a ball valve so I can manually bleed it or put an air bleeder there to try to make sure the air stays out of the top of this, because if the top side of this evaporator does get air stacking, it will create these exact conditions. That'll, similar to the oil stacking, it'll cause a lack of heat exchange. And even though you'll have good DP, I've had this happen. It's the craziest stuff, and it can be a pain to troubleshoot the first time you see this. You'll have perfect DP on your evaporator. It'll look great. But you're not actually making full contact with all the water in the circuit because the air has gotten trapped in there. And that is causing a higher approach with low suction pressures as an issue. So you'd be shocked how often this is a problem. Even if there's air bleeders close to the chiller, in the piping itself, right? Just because the piping has air bleeders in it, these evaporators make excellent air separators. I mean, they're amazing air separators. And so, I mean, because of the baffling in here. So keep in mind, like these evaporators, there's baffling inside of there that the piping, that the water flow is going through as it's not how it go like this. So all of these little choke points up here, this is like, it creates a perfect turbulent spot for that air to just stack in there, which is where having bleeders up on these ports can be really, really useful. So I'd highly recommend maybe looking into that. Isolate that evaporator, shut the chiller down first, please. Then isolate that evaporator, and even if you just put a ball valve up there, typically these will be a 1/2 inch threadlet that you can thread a valve with a nipple into. And you can, if you put a ball valve in there, you can always add an air bleeder later, like a Hoffman bleeder. You can always put that on later as long as there's a ball valve there. So I would just suggest start with that, and then see how much air may be in that evaporator. It may not be the problem. It's just a option on the table. Could be air stacking, could be possibly oil stacking. If it is oil stacking, again, that's going to be from a low load over an extended period of time. So either increase load, like that is the best thing in my opinion. Just get the load up on that machine. As it loads up, it's going to increase the velocity through the circuit. That higher velocity is going to allow that oil to return back. You're going to see these numbers improve with runtime. And while you can make an argument that we would expect to see this across multiple chillers if it was something like a low load issue, that is true, but it also gets into just the nuance of sometimes weird things happen, and it comes back to how each chiller ties into the load and the water flow. Just because there's 5 others doesn't necessarily mean they're all for sure going to have the same symptoms, and it comes back to where is that chiller at on the header that affects how the water goes through it. And it could be affecting that chiller just slightly more, right? It's possible that the other chillers have just enough turbulence and GPM through them where they're not having that stacking issue where the others are, or this particular one is. Question. Let's see, let me kind of catch up on some of the it's a big ass dream, Jason. Okay, how you doing, Darren? always get mixed up because I hear your name pronounced a few different ways. So I never know which way it's supposed to be said. Yeah, that's what I'm gonna stick with. Okay, what other options do we have? We have air trap, oil stacking. If we show good DP across the evap, we know it's clean. We know the charge is good. The only other option I could think of is be the metering device itself. If the metering device is starving the evaporator, you're not giving it enough refrigerant, that's going to cause similar issues. You can still have leaving water set point being made. It may not be a complete failure on the metering device, but it's failed just enough to cause the saturation issue. Like, that is possible. Yeah, that's absolutely a option. So if we're not oil stacking, if it's not air in the evap, then I would then look at the metering device. Those would be the three main areas that I would want to be focused on. That's where I would go to troubleshoot this particular problem. So just kind of going back for a quick review. Yeah, so explaining low suction pressure on a screw machine, but with normal discharge pressure. One of the things that I do want to point out in closing this, keep in mind the discharge pressure is going to be relative to the ambient conditions, especially with an air-cooled system specifically. So if you've got a higher ambient, just because you've got low suction pressure doesn't mean that you are automatically going to have really low discharge pressure. The discharge pressure responds directly to the amount of heat being inputted into the evaporator. So the more heat the evaporator is taking in, the higher the discharge pressure will be. So just, even though you're having a low suction pressure at this moment, you're still making set point, which means you're still taking in enough heat to hit set point leaving the machine. So you may be suction limiting. You're at the low end of what that machine should be running at. Like you're right there at the trip point, but you're still taking in heat. It's not doing it very well, but it's happening. So what that means is that your discharge pressure is still going to look relatively normal, because it still just has to reject however many BTUs the compressor takes or the evaporator takes in, and however many BTUs happens in the heat of compression and inside the compressor. Those two things are what the condenser has to get rid of. So when you see a scenario where you have a low suction pressure but your discharge looks normal, keep in mind the fundamentals of what is making that condenser and that discharge pressure work, and why the pressures are what they are at that given time. It is a very, very important fundamental that we have to keep in mind in this process. Stream and equipment work, yeah. Anyone know anything about... Nah, Shrek, I don't, yeah, so just that specific model of purge. No, but we can follow up if you want to send me something on it. I might be able to find some material, maybe help you to kind of talk through it. Purge is a purge at the end. Like, they've all got their little nuances, don't get me wrong, but it's still just a purge for a low pressure machine. So you just send me an email outside of this, Shrek, and we can talk through that. Let's see. I think we had a couple of other... There was one other question I definitely want to just hit real quick. Subcool temperature. How to take in chiller. Yeah, subcooling is going to be measured via the liquid line the same it would with a regular RTU or split circuit. We're going to take liquid line saturation, liquid line temperature. There's your subcooling. Be careful in the event that you have a braze plate economizer or just an economizer in general. In those systems, I always take my subcooling before the economizer, not after. So if you do have an economizer, take that reading before you get to the economizer. You want to take the subcooling actually leaving the condenser coils. And that is what most of the literature will be. If they give you a subcooling value, that's what that value is representing. This is pre-economizer subcooling, not post. Why suction pressure transducer go bad on turbo core? I've seen them going bad. Any other issues? Once a year. So close to the compressor. Yeah, I've not seen that in my particular with turbo cores. I've not had a routine issue with the suction pressure transducer. Maybe that I'm not as to why that would be a routine. I'm not sure. If it's happening on the same compressor over and over, maybe that the power control circuit or the backplane board is having an issue. It's overvolting or undervolting that transducer maybe. So that could be the root, is whether it be the DC to DC converter or the, I'm talking to Tejas here, his question a little bit earlier. So either the DC to DC converter or the backplane board may not be working correctly. It's causing that specific transducer's power feed to fry the circuit routinely. That would be like a possible extreme scenario as to why that machine or those machines could be having an issue, whereas that's not something I've routinely had to deal with outside of that. Okay, I do need to be wrapping up. There's one other question I want to, Caldwell here, James. Centrifugal chiller. Do you clean both ends of the condenser barrel? How often should you clean the evaporator barrel? I'll finish up with this question and we're going to wrap this up. So you don't need to clean both ends of the condenser barrel. You can just clean the one side. Usually it depends on if it's a single pass, 2-pass, or 3-pass. Most machines are a 2-pass unless it's like a high efficiency or something. In the 2-pass, we usually open the closed side of the shell unless it has a water box where it has a hingeable door. So when you get into much larger machines, you'll have a water box with a hingeable door. Smaller machines, they'll just be a set of pipes connected to the end of a compact water box, as it's referred to as, or an end bell with the water connections. Usually on those smaller ones, we're not going to open the piping side. We're just going to open the other side where there's no pipes at all. If it is a 3-pass machine, I highly doubt you're going to run into very many single pass. So if it is a 3-pass machine, you'll just have to pick one side and disconnect the piping on that particular side and open it up. It becomes much more of a pain at that point. But unless there is a reason to, like if we got to go in and plug a tube, say we diagnose a tube is bad, then yes, you have to open both ends. But other than for something like that, or if there's major corrosion or something inside the heat exchanger, you don't typically have to open both ends. If it's just a standard routine condenser cleaning, just open one end, whichever end is easier at that point, in my opinion, and brush the tubes from top to bottom. Make sure you are aware of the type of brusher you have, the size of the brush to the tube bore. Like there's a lot of details. I do explain those details in the certification course at Chiller Academy. So if you are enrolled in the cert course, go look at the tube brushing, and I talk through the brushes themselves and like how to choose the brush you're looking for. In terms of, and you would do that on an annual basis, right? So that's recommended specifically on open loop systems. There are closed loops, but on open loops, it's recommended to do that at least once a year. If it's a closed loop system, then this is also where we get into the evaporators. Almost all evaporators are on a closed loop. Only some process systems are going to run an open loop evaporator. If it's a closed loop, You only have to really worry about doing those tubes every 3 to 5 years. That is true for the condenser or the evaporator. So every 3 to 5 years, you'll open those up on a closed loop and you'll brush those out and do an eddy current. Again, that's every 3 to 5 years. You'll do the evaporator in the exact same way you would do the condenser. Typically, those are 2 pass. You'll have one side that has no piping connected. So that is the standard that we go by in the industry, is based off of just what type of loop is it, open or closed. Open loops get every annual at a minimum. Some sites need more than that. And then you will do an eddy current every 3 to 5 years, depending on the site. And then closed loops will be open up every 3 to 5 years in conjunction with that eddy current testing. And on an open loop system, the only time you truly need to open the other side is if there's a problem, you need to plug a tube, something to that effect, or you've got a significant amount of trash you need to clean out of there. That would be the standard that we will go by. Excellent. Holden, are you going to have any other in-person training sessions in the future? I will. I am planning, so this is the official kind of first trial launch, if you will. We've got a lot of details I'm working out along the way, but I do plan to do another class in March and April, and I am looking at doing these up to maybe 4 times a year, at least here in the beginnings. 2 in the spring, 2 in the fall is kind of what I got in mind. So if for any reason you can't make this fall class for November work, you've always got March and April that you can get booked for. I will get details on those March and April classes posted towards the middle of November is my current plans, and we'll discuss that much further then. With that, MTT, everybody, make the time for your family, for your spouse, for your kids. They really need you. We don't have the time in this industry. We have to make that time if we're going to do it at all. Be sure to do that. Stay safe out there. Take care of yourselves. Have a great week. Really love today's chats, and we'll see y'all later.